Thank you so much for coming. This is going to be our last section. I forgot to change that to a 4. Thank you so much for coming here again this week. And today we're going to be talking about recurrent neural networks. But before we begin, we just wanted to see if anyone had any questions about what we covered last time in terms of the convolutional neural networks. Today's going to be slightly, like you could have missed the last one and still probably understood this, so it's not going to be dependent on you understanding the CNN entirely, but if anyone has any questions, like lingering questions about that. Okay, then we'll just get right into what we're going to be doing today. So the key use of recurrent neural networks is being able to deal with sequential data. And most things that we see in real life, things like when we read text, order matters. When we see video, order matters. And so I'm going to give you an example here of 2 images that a convolutional neural network might think, if we ask them to classify what sport is this person playing, they might have trouble differentiating between the 2. Because you're looking for localized features using filters, so it might say, okay, there's a hat-like thing over here, there's also one over here, there's some long, oblong thing that's diagonally oriented, they're both wearing a belt, things like that. So from a still image itself, it's very hard to tell. And so the way people sometimes get around this, but still use CNNs, is that they just classify frame by frame, but then enforce that the classification between 2 consecutive frames, for example, can't wildly differ. You can't have one person playing baseball in one frame, and the next frame there's something playing golf. But the thing with this is that at every frame, even if I took this, imagine if this was a video, if I went back a few frames, forward a few frames, and I did the same for that, I still wouldn't be able to solve the problem. I still have the same issue, where the filters would identify all the same things. Because there's still going to be this, the belt, there's the arms will be sort of up here, things like that. And so the key difference here is that if in golf you're hitting a stationary ball, in baseball you're hitting a moving ball, and so as soon as you see that white ball move, then you know which one it is. So so today we're going to be covering a structure called recurrent neural networks, and these are going to keep track of information over time. And so the network will be able to sort of keep track of the fact that, okay, there's a white ball, there's going to be a white ball in the video, so I'm playing golf too. But the fact that it moves, hopefully you'll be able to keep track of that, and that will be the key the key difference between whether someone's playing baseball or if they're playing golf.
So up to this point, all the types of neural networks that you've done have been a category called feed-forward neural networks. And basically what that means is that when you draw out all the little nodes and lines in the graph of the network, there aren't any loops. So in your CNN, the second layer of the CNN doesn't feed back into the second layer of the CNN, right? You go from first to second to third. There are no loops in that entire diagram. However, the special thing with RNNs is that there actually are loops in RNNs. And so what this essentially means is that there is a state associated with the RNN. And what this state is doing is it has some memory about what it's seen in the past. And so essentially the state is going to be a vector of a certain size, so let's say a vector of size 256, and the network is going to learn how to update the values in this vector depending on past data, so that it kind of summarizes all the data that it's seen in the past. And so at each, let's say if this was doing video classification, then X would be your frame of the video, H would be your state, and the state would have summarized the past information from the videos. And so what would happen is there would be some function that not only uses the current frame of the video, but also uses the state vector. And so what that does is it also gives you information about what happened in the past, and you can make better predictions because of that. So in this case, the way that this works is it's actually pretty simple. In a way, it's simpler than a convolutional neural network. And so essentially what we've got is we've got some input X, and we transform it with a matrix U, and then that generates some vector. And then we also generate a vector based on the state H. And that uses a different matrix W, and that also generates some vector. And then you add those two vectors together, and then feed that into your activation function, and that's what gives you your actual output. And so, and this is the way that you update the state. Just to clarify, the state, this is the formula for updating the state, and then in order to get the actual output, you take that state and you multiply it by a new matrix V. So this isn't your output, this is just how to update the state. This bit up here is your output when you take the state and multiply it by V. And so this is kind of the simplest type of RNN that exists. We're actually not going to be using this today in the coding portion. We're actually going to be using something called a long short-term memory cell. And that's more complicated, and we won't be covering exactly how the math of that works, but we can link to some articles if you guys are interested. What we're really emphasizing today is just understanding why you would use an RNN, what the state is doing in an RNN, and like what the advantages are, and how to think about the flow of data through an RNN. So that's what we're emphasizing today. So this formula up here is for a very simple RNN to give you a concrete example of how this might work. But really the whole concept of having a state and an input for every step, or having a state and an input, and then computing the output based on the state and input, that applies to any RNN. It doesn't matter how complicated. So, so essentially, an RNN is really good with sequential data. So the whole point is that it starts at the beginning of, let's say, a video feed or a sentence, and it looks at that unit by unit, or element by element. So it could be a frame at a time, it could be a word at a time, it could be a character at a time. And what it does is, it's going to generate some output for every step in that sequence. So essentially, for example, and there are a couple different ways that you can do this. So for example, you could have a RNN that is a one-to-one model. So the horizontal axis here is time, or like sequence. So for example, if we were doing a video feed, the left would be the first frame, this would be the third frame. If we were doing a sentence, this would be the first word, second word, third word, or first character, second character, third character. So that's how to read that. The squares on the bottom are the input vectors. These are the states, and then these are the output vectors. And so what's basically happening is there's a whole number of different ways you can apply an RNN, and depending on the problem that you're trying to solve, your inputs and your outputs might look a little bit differently. So one type of RNN is one-to-one. Right, so you're right. So, I mean, it technically could be, but yeah, just one-to-one is basically what we've done so far. So, let's say you take a frame of an image, or if you wanted to use a CNN on an image, what you could do is you could look at it with one frame, do some classification on that frame, and then it'll produce an output. And then the next frame, you'll do that thing again, but it's completely separate from the previous frame. It has no information about the previous frame, and so, for example, your classifications might totally jump frame for frame. One frame it might detect a cat, the next frame it might detect a dog, and the next frame it might be back to a cat. However, if it had some information about the history of what it's seen, it wouldn't make those jumps, in theory. So, with all the CNNs and the feed-forward neural networks and the linear classifiers, they all take a single input and they produce some single output. And so that's a one-to-one model. But RNNs are going to allow us to do something more complicated. So for example, we might say, okay, we want to take a single image of a dog, or just some image, and then generate a sentence describing what it sees in that image. So for example, in this case, your input is just one image, but your output is a whole sequence. And so this might be the first word, the second word, the third word. And as you can see, the state also goes along with that. Another example could be, suppose you want to classify some sentence. So maybe you're looking at a food review, and you say, okay, I want to determine whether this food review thought that the sentence, that the food was good or that the food was bad. And so your input is a sequence down here, but your output is just one thing, good or bad. And so this is a many-to-one architecture where every time step gets looked at, fed into the RNN, and then at the very end it just generates one output. There's also two different many-to-many sequences or structures where, for example, if we want to generate text, we could say, okay, we will feed it the text and then tell it that we're done feeding it the text, and then it will start outputting the text or outputting some change. So like that might be, you want to feed it a sequence and then you want it to output the exact same sequence, or you want it to output some new sequence. And then in this one, it's the exact same concept, except now instead of being offset in the time dimension or in the sequence dimension, it's just right at the same time. So this one at the very end is actually the one that we're going to be doing today. Essentially how it's going to work is we're going to have a sentence that is 25 words long, and it's going to be from Alice in Wonderland. And essentially we will say at every single step in the sequence, we will try to get the network to predict the next word. So at time step t, or let's say the first word is hello and the second word is Bob, then this should be Bob, this should be hello, and this should be Bob. So we're essentially shifting, here's our input sequence and we're going to shift it over, essentially. So time step t, it predicts what the output will be at time step t plus 1. Before I continue on, does anyone have questions about this whole concept of like state and why you would use an RNN versus why you would use a feed-forward neural network, or just any questions about what I've discussed so far?
Okay, so how exactly are we going to train these networks, right? We've been talking about using back propagation, where we're going to feed all the inputs in, calculate all the values of each of the states, intermediate states, and the output, and then propagate the gradients back from the outputs to the inputs. But with a loop, right, it's going to be very hard to do that, because if I just have something like this, and I want to feed in the input, and then I feed in I calculate the intermediary step here, but then I loop, and then I loop again. I don't know how long I should loop for, and what all the intermediate values should be, how those affect the gradient. So that becomes very, very difficult to do. And so what we do is we do what's called unrolling over time. So what we're doing is that we're just representing each time step sort of vertically like this. And so now we have inputs each time, in state each time, output each time, and this is, now we've got a structure where we have no loops. Now this is just a feed-forward neural network. And so you can think of this diagram as being sort of like a sideways version of what we've been looking at before, where this is the input layer, this is the a hidden layer, and that's the output layer. And so now we can use the exact same training algorithm we've been using the whole time, which is using gradient descent, using backpropagation. So what we do is we decide on a certain amount of time that we want to unroll our RNN for. So in this example, we've decided to unroll our RNN through 3 time steps. And so now we have we just have a fully connected network where we have an input layer size 3, hidden layer size 3, and output layer size 3. And the only real difference between this and a fully connected network is that because these aren't actually different things, they're just the same thing at a different time step, we're now mandating that this weight here and that one and this one are all the same, for example. So like these U's have to all be the same, these W's have to all be the same, these D's have to all be the same. So this would actually be much easier to train than a fully connected network of the same size. And so this is sort of the same diagram that we've been looking at here, where we're unrolling the graph over a certain amount of time, and we're just creating a feed-forward net structure where there are no loops anymore. And we're just dealing with time as sort of like an axis along which we're going to unroll the graph horizontally, and then our layers are sort of vertical from the bottom up, from input to output. Does that make sense? Okay. So the RNN that we're going to be using today is going to be a stacked RNN. So what that means is we're going to have multiple hidden states. So, for example, you could think of us having like another green layer on top of here that connects upwards from these, and then sort of more intermediate steps, so that our RNN can keep track of more things and keep track of things in sort of like a different way. So.
So just to elaborate on the stacking of an RNN, let's kind of take a step back and like think about some of the fundamental limitations in this structure right here. So when we discussed fully connected neural networks, we said that as you add layers in your fully connected neural network, then you're essentially going to be able to approximate more and more complicated functions that are extremely nonlinear, right? So again, in the very first lecture when we covered linear classifiers, they could only essentially they could only draw planes through high-dimensional space and separate data like that. But when we covered fully connected neural networks, they could draw all sorts of crazy functions in high-dimensional space. And that was kind of the whole incentive for using fully connected neural networks. And so when we unroll this, we are essentially getting a whole bunch of different layers. But the problem is that each of these layers do the exact same thing. They all have the same weights in each layer. So that means that whatever transformation function there is from here to here is the same transformation function as from here to here, and from here to here, and from here to here, and so forth. And so that's kind of not necessarily something we want, right? Like, it's not necessarily true that I can update the state properly with just essentially the operation that a single layer of a fully connected neural network would do. In theory, I might want many layers worth of computational power just to update the state and just to compute the next output. So what we can actually do is, so this is a single RNN cell here, but what we can actually do is we can have multiple RNN cells in like one single time step before we enroll. So to explain this a little bit further, suppose I'm going to draw what the graph looks like before we enroll it, so it's going to still have loops in it, and that should help to demonstrate what the difference is. So, for example, we might have some cell here, and it has some. So the first graph that we showed looked like this, right? You have some input, some output, and some state. Okay, well now what we're going to do, if I can find an eraser, don't mind me. And just to remind you, this is limited because there's just one function that can update the state, right? This is equivalent to like one layer of fully connected neural network that can update the state. That's what this arrow here is doing. And so what we really want is we want something like this. Okay, so what you're looking at here is you have one input, right? And this is for a single time step. So this is the time dimension, so this is a single time step. So these are all operating on a single word or a single frame of the video. So what you do is you take your word, let's say, and you do the same type of operation that you do up there. I guess I covered it now, but could you go back to the math slide? Yeah, okay. And you can see that, I'm sorry. Okay, so you're going to do the exact same operation. But now, when you take your W and you take your O, when you take your H and you take your O, this is H and this is O. And so now they're getting passed into another RNN cell. And so now, this is operating, instead of on its own state, it's operating on the state of the previous RNN cell, and instead of the original input, it's operating on the transformed input, or in other words, the output of the previous RNN cell. And so essentially when we unroll this in time, now what we get is something like this. This looks pretty complicated, but that's what it's going to look like. This is pretty small, so I hope you guys can see this.
It looks complicated because you've drawn extra lines. You've drawn the state line from the first hidden state to the second hidden state.
Where? Did I actually? Yeah, because this is in one cell. So the key thing is that like this cell, so what we're essentially doing, sorry, I should have finished. So we go from this state, the way that the state travels is it goes from this cell to this cell to this cell, and then it loops around. So in the original one, it just loops immediately, right? But in this one, it goes from the first cell to the second cell to the third cell, and then it loops. And so when we actually turn this into, when we actually unroll it, so this is a time axis, that means that it goes from the first cell to the second cell, and then it loops. So to loop it, we put it back into the first cell, right? Okay, so before I continue, this is kind of important. So like, can everyone even see this? Do you guys have questions on this? It's like not necessarily the easiest thing to wrap your head around, so like, please ask questions. Okay, all right. You guys must be geniuses then if you have no questions on this. Yes?
Is it three of that all represent the second part?
Three of which?
The two layers in the third part.
Here?
Yes.
Yeah. Also, just, I feel like I should mention, I drew 3 here, but I only drew 2 here. So really, if I wanted to be honest, this is the output, right? And so it's like that. So just to keep it consistent with what I drew here. Is that what you were asking? Okay. Yeah. I realized that if I drew 3, it'd get like super messy very quickly, so that's why I didn't do that. Okay. So in this case, there are only 2 ornament cells. Does anyone else have questions on how this works? Okay, great. Yes?
I'm not quite sure because each circle you draw here is actually like a function that takes input and got output, right?
Mm-hmm.
And here I saw in your second graph video, and what do you mean by the O in the center? I saw this. Like the line between 2 circles, and that line is that some output or some functions?
Yeah. So this is what we want to generate at every time step. This is, so for example, in the sentence, this is our next predicted word. This is our current word that we're looking at right now. And then this is the flow of our state. And so, and this line right here, this is an intermediary output, right? So in this case, this line right here is that output up there, except instead of just immediately going to the output and we say, okay, that's our prediction, we then feed it into a new ornament cell. So I don't know if you can see the projector, but basically this line here is that line here. And so, but there's another of these up here, right? So we want to pass that into the next one's input. Does that make sense? And that's separate from the state. So there are outputs. Each RNN cell generates an output and it generates a state. The output is usually what you're using to make your prediction. But in this case, we're saying, oh, we might want to pass it through another nonlinear transformation before we generate the prediction.
So what is the difference between
Which ones?
In your center, in the central graph, like what is the difference between the N line
This one and this one?
and that?
This,
Yeah.
this one and this one? So this is the state, and this is the like intermediary output, right? So in that, this line here is this, that's the state. And this line here is this, which is the output. And in this one, we were only using one RNN cell. And so we got the output and we were finished. We said, okay, that's our output, like we're done. But in this case, we're saying, no, actually, we want to do a more complicated function. It might not be powerful enough. So we want to add another layer of computation on there. And so that's why we then do another state and another output. Yeah, so there's one state here. This is the state from the first cell, and this is the state from the second cell.
Where is the draft state?
It's this big because it has to loop back into the beginning.
So there are two draft units.
Yes, there's two U's, two V's, and two W's. But in one of these lines, right? But the U's, V's, and W's may vary here, but they don't vary horizontally. Okay, so this U and this U and this U are all the same. This is a new U, which is the same as this U, which is the same as this U. And same with the V's and W's. And so does that make any sense? Yes. Okay. Yes.
But you have to be fairly certain of of a certain cyclic behavior of your data if you apply such a neural network structure to it.
So the whole point of why you would use an RNN is you say that the sequence of your data matters. So it makes sense to only look at it like in a particular direction. It's like in a CNN, when we look at an image, sure, we're scanning the filter over the image, but at the end of the day, it just produces one result. And so it doesn't matter which order you scan the filter over the image, right? I could start at the top left and then go to the bottom right and then go to the middle, and at the end of the day, it's just producing the same result. It doesn't matter what order I scan the filter. But in an RNN, obviously we don't have filters, but what we are doing is we're looking at each element of our input one unit at a time, and then just taking it one piece at a time. And we generate a state. And so essentially, if we have a sentence, like if there's a sentence drawn on the ground here, then like I start at the first word, I do some computation, then I go to the next word, I do some computation, and then I go to the next word, I do some computation. And all the while, in the state vector, it's remembering what it's seen in the past. It's not necessarily just like copying what it's seen in the past, but it's getting some sort of embedding or some sort of vector that summarizes what it has seen in the past. And so as it goes through, it continuously at every time step uses that summary vector, also known as the state vector, to, as well as the current word that it's looking at, to make some output. So in this case, that state that it has is for both of these vectors. So it uses them in a couple of intermediary steps, and at the very end it produces an output based on one input and these state vectors. Okay. Oh, yes.
I'm confused by the fact that you draw two arrows, two edges, from the first node to the second node in this.
So this and this.
Yes.
Right.
Why just
So up here, the state is separate from the output, right? And that is because our state is just a summary of what we've seen. Our output is our actual result. And so, but it might be that, there's only, the function that generates the output is just v times the state. And it's not that complex of a function, right? That's equivalent to one layer of a fully connected neural network. But we wanted the computational power of several layers of a fully connected neural network. So in order to do that, we have to have several RNN cells. And so if this wasn't here, that would just be the output and we'd be finished. But we want to have more computational power, basically. And so we then take that output and treat it as the input of the next RNN cell. And we treat the state of this as the input state to this RNN cell. And so that's why there's two lines. There's one line for the state, and there's one line for the intermediary output. Yes?
I'm still sort of confused about if the intermediate output and the state are separate, why are they going to the same node?
So in theory, the network will learn that, like, their purposes are two different things, right? The input slash out, like the output vector is supposed to be your transformation of the input data. Your state is supposed to be a summary of the input data and all the previous summaries.
Okay.
So that's why you have two separate things.
So they're the same function, but are they going to be represented by the same function?
So
the same
for
way?
the type of RNN that we showed, I'll go ahead and lock my computer real quick. The type of RNN that we showed, yes, it's basically just the same function. It's just some matrix multiplication with a nonlinearity, just like fully connected net is. Like you see here that although these two matrices are different, right? Although U and W are different, it's still the same type of function. However, there are RNNs that are much more complicated, and they'll do crazy things to the state that are different from the input. So that's why they're separate, though, because presumably the network is going to learn that the state is supposed to be a summary, and the output is supposed to be some transformation of the input.
Okay, so it could do them. It could actually do a different
Yeah.
different function with different weights for that.
So, and the weights are definitely going to be different,
Okay.
because they're separate matrices. So, okay. Are there more questions on this? Yes.
Say a little bit of prediction that is 5 times 6 per now.
That is what?
Like I want to predict something that is 5 times 6 per now. Like in the present state, I want to predict something that is 5 states per now. It's like 5 steps ahead.
So you're talking about doing something like this?
Yeah, something like this.
Okay.
So how would the looping be then? Like,
So the looping would still happen. It would still happen in the exact same way. But now when you fit your loss function into the model, we actually, let's discuss that in just 1 second, okay? Does anyone have any more questions about like how multiple RNN cells work? Okay, all right, so then I can go into the loss function. So you may be looking at this and you may be thinking, okay, well that's all well and good, but we should have labels associated with these, right? So like in CNNs and in RNNs, there was always some label that we used to compare our predictions and our labels, and then that went into our loss function. And so the way that this works in RNNs is still the same concept, but the way that you kind of plug all those numbers in is a little bit different. So essentially, this one is the easiest to understand, right? There's a label, presumably, for every blue box. And actually, for all of these, there's a label for every blue box. And so in this one, you just have a label at every single step of the sequence, and then you compare that label to the output using your cross entropy loss function, just like you always have, and that generates some scalar value that tells you how badly you're doing. And then you just take the average of all those, and that's your loss value. However, what about this one? You have inputs here, but there's no outputs here. But we're not changing the actual structure of the network. It's just like, this is still generating an output at these time steps, except we actually don't care what that output is. And so the simplest way to say that we don't care about the output is it just doesn't go into any of the math that we use for the loss function. So we just don't have labels here, and we're not comparing anything at these time steps. We only start comparing the output and the labels at these time steps. And so concretely, what you essentially do is whatever output the model generates at this time step, you'll just multiply by 0. And that will set its gradients to 0, and it means that it will just have no effect on how the network learns. And this is called masking, when you just put zeros in the spots that you don't care about. So for example, if you're doing a question answering problem, where maybe you ask a question, and then you want an answer, and then you ask maybe another question, and then you want another answer, the places where the network isn't supposed to be responding, you just put zeros in all those time steps for the loss function. Okay. Did that answer your question?
Yeah, and also, how is the loss function computed in an RNN? Like, do you compare the output at one state with the input that you're giving in the next state?
Yeah, so the state doesn't get factored into the loss function at all. You only look at the outputs when you're looking at your loss function. So for a single, like, so here is your conventional like CNN or fully connected neural network, right? There is one output and one label. Well, in our RNN, we'll have many outputs and many labels. And there will be a label for every single time step, or for all the time steps that we care about at least. So if you have an input sentence, and then you say, okay, we're finished with the sentence, now generate a new sentence, then you won't have labels here, and you'll just multiply all these by 0. But you will have labels here, and then for every single label comparison, you do a cross-entropy loss function. And that generates a whole list of scalar values. And then you just take the sum or the mean of those values. And that gives you your final loss value, which is just a scale. Does that make sense? Okay. So does that explain like how you do the loss function? Do people have questions on how the loss function works with this? Okay. I'm gonna move this out of the way now.
Okay, so now we're going to start talking about the problem that we're going to be doing today, which is the task of generating some text. So Ryan mentioned that we were going to try to generate text sort of in the same like style and content of Alice in Wonderland. So it's just like writing sentences that we could theoretically just stick into it, and it would not look out of place. So when dealing with text data, obviously this is a very clear application of an RNN because word order matters. Even though, just as a side note, it's often very, very difficult to actually beat models that don't take word order into account at all. Those are called bag of words models, where you just look at what words are present and you don't actually care what order they're present in. And it can actually be very difficult to beat models that just look at, okay, like the sentence, I like neural networks. It doesn't matter what order those words come in. So the way we encode text data into, so obviously we need to feed in the vectors and tensors into our neural network. And so the way we do that is we create one-hot encoded vectors of a fixed vocabulary size. So we're just going to say, pick maybe 1,000 or 10,000 English words that we're going to deal with and put a 1 in the place of the word that was present and then zeros everywhere else. So like I have a vocabulary size of 1,000, and like the first index of that corresponds to maybe the word the. Then the word the becomes a vector with a 1 in the first place, and then just 999 zeros. And that's going to be the same for every single word. It's just going to be a very long vector, tons of zeros, 1, 1. And obviously, because we are dealing with a fixed vocabulary size, we can't actually encode every single word because there are just too many. And when you're dealing with something with Alice in Wonderland, for example, words like names that don't come up very often, or just like strange words, unique words, we're not going to be able to encode all of them. And so we save a token called an unknown token. So that's just for anything that wasn't included in our vocabulary. And a lot of the time, when you're dealing with a large chunk of text, the unknown tokens will just be things like proper nouns, names of places, or like names of people, because we haven't managed to fit that all into our vocabulary size. And so if we learn to treat all these unknown tokens as the same, it actually comes out to sort of represent things like a proper noun or something like that.
Just to clarify though, it's still represented the exact same way as it is any other word. So we may have written bracket unknown, but that's just how we're going to represent it when we actually look at the results. It doesn't mean that that's how it's actually stored in the network. It's still stored as a one-hot encoding. There's some dimension in that encoding that represents some index of that encoding that represents the unknown token. And there's just going to be a 1 at that place and 0 everywhere else, if it's unknown.
And so we can also do the same thing with the beginning and end of sentences. Instead of marking sort of like a period, we just mark start of sentence, end of sentence. And as before, we just have an index in our vector that corresponds to a start token or an end token. So we'll have an index that might be corresponding to the, hello, it, Ryan, and then a token for unknown, like a location for unknown, a location for start, a location for end. So the problem that we're dealing with is a text generation problem. So this is obviously a many-to-many problem because the input is a sequence of text and the output is also a sequence of text. And so each time step, what we're doing is we're predicting the next word that should come. So given the word like hello, what should be the word that comes after that? And then in that context, after hello Ryan, what comes after that? And we just keep going. And so the way you can do that is you can actually do RNNs at the character level or at the word level. We're going to be using a model that operates at the word level right now, so we're just going to say what word should come after this. But this is an example of something using a character level RNN. And you can use these, for example, where these are being used to generate things like code that compiles properly. So following specific syntax rules. Like if you open a parentheses, you have to close it. You have to open like 2 brackets and you have to close both of them. And you have to close them in a specific order such that one of them doesn't, you can't close the outer one before you close the inner one, for example. Or like you have to have semicolons at the end of lines, for example. And so there are some cool applications where people have managed to generate useless code, but code that will compile properly given tons of training data of code that will compile properly.
People have also generated like text files where they'll come up with totally fake mathematical proofs. If they generate source code, oftentimes you'll find that at the beginning of every document, it'll have like the copyright notice. So they're actually like surprisingly good at like detecting patterns and recreating patterns. And as you'll see today, the RNN that we actually write will remember exact sentences from Alice in Wonderland and recreate those perfectly. It'll also generate sentences that are pretty bogus and like aren't passable sentences. But presumably more complicated. The more complicated the model gets, the more powerful it is, and the more realistic you can make.
The math proof one is actually quite funny because the text sounds very intelligent. They use like fancy words and they'll say like hence this, and they'll lay out some reasoning and say therefore that. It's just that conclusion they come to will just be like completely false.
Okay, so we're actually, like, the theory today is like pretty short, and that's because the implementation is pretty complicated. So I'm going to be going over the implementation now. If you guys have more questions on the theory, you should ask it now rather than later. Yes?
So when you unroll this, is it as wide as the number of elements that the RNN is looking at simultaneously?
Yes. So obviously, like, this could recur forever. There's nothing in this structure that means that it has to stop at a particular time step, right? But, so like, let's say your sequences are thousands of units long. Well, this would have to be, you would expect that this would have to be thousands of units long along the time axis, right? However, computers are finite, and there's only so much computation that you can hold in memory at a time until it basically just runs out of memory. And in fact, the RNN today that we're training, even though it's simple, even ran out of memory on my laptop a couple of times. So what you have to do is you have to say, okay, well my sequence may be like 1,000 units long, but I'm just going to unroll this for like 25 or 50 or 100 units. And then, so what that means is that when you do backpropagation on this graph, it can't detect, I mean, it can sort of detect time dependencies longer than the sequence that it's in, but to be 100% accurate for that gradient descent, it has to be within your unrolling length. So, so for example, suppose your average sentence length is like 30 minutes long, then like 35 might be a good number to use for your unrolling length. And technically it can still learn dependencies a little bit longer than that, but they just won't be like 100% mathematically accurate, and then the farther it goes, the quality just totally degrades. So, yeah.
As a side note, if you have variable sentence length, for example, you can encode a sentence of length 10 as a sequence of length 15 because you can just stick empty words at the end. whereas if you had a longer sentence, you have to chop it up into two.
Yeah. And so that again goes into the concept of masking the loss function. If you only care about the first 10 inputs, because your sequence is only like 10, but you enroll the graph to 25, then the next 15 inputs, you'll just multiply the loss values by 0. And so that's how you handle sequences that are shorter than your enrolling length. Again, if they're longer than your enrolling length, you just have to chop them up into lengths of your enrolling length and then feed it in.
And that's where you get like an input that doesn't start with a start to it, for example, because it's not the start of a sentence, it's like a continuation to the previous.
Okay. Okay. Any more questions? Yes.
So if you're chopping up your inputs because you have to break things up, then the output, is there a way that it concatenates it back together, or do you have to do that like?
Yes.
after the fact?
So at this, okay, so the very end of this, you get an output and you get a state vector, right? And so what you can do is you can chop the network off here, but you can bring that back into Python and then feed that in as placeholders in TensorFlow as the next. So like the state doesn't have to start at 0, it can start at whatever value the state was previously. And that's why the network can somewhat learn time dependencies that are a little bit longer than the length, but it's not like 100% accurate anymore. But, and once it's trained though, you can generate infinite sequences. Like you can always just use the previous state and whatever current input you want to generate the next one. You can just do that ad infinitum. Okay.
Yeah.
So is it necessary to send one word at a time, or can you send a batch of words at a time so that way you don't have to have so many?
Yeah. By the way, can everyone hear when people ask questions, or should I? I'll just repeat them. So what she said is, do you have to do one word at a time, or can you use a batch of words at a time? So to answer your question, we can batch in the same way we batched in CNNs, fully connected networks, and in fact we do that in our code today. Is that what you're asking, or are you asking like actually understanding multiple words at a single time step for the same output?
No, well, I was wondering if you could send a batch of words at a time at each time state, so then that way you won't have the problem of like having too many states.
Are you talking like about a batch of words, like a batch in the context that we discussed it before, like a group of words, like hello, I am is one thing, and then like Ryan Butler and.
So, like, are you talking about like computing things in parallel, or are you talking about like this is one object that we're like using?
Like parallel with a binary entitlement, sending like one batch of words at a time, and then computes an output with that which goes set of words.
If you are,
I'm still unclear on whether you're talking about feeding. If I have this sentence, this sentence that says using an RNN to generate text, right? Are you saying that I would feed this in, right? Like say using an is input at time 0. RNN2 is input at time. Is it that what you're saying?
Yeah, I'm saying like using an RNN could be like one.
okay, so that is different than batching. Batching is when you have two separate sentences that don't have anything to do with each other, and two separate labels that don't have anything to do with each other, and the only reason why you're running them together is for like to utilize the parallel nature of the GPU. What you're asking is like actually group two words together and treat that as like one input in here. And so yes, you could do that. What you could do is you could concatenate whatever embeddings are generated by those words. And then that's one way to do it. You could also just like have an additional, a whole nother dimension. Like now instead of these being vectors, they could be like matrices and do that. And that's like now something that diverges from the classical way that RNNs work. And there's no reason why you couldn't do that. It's just a question of empirically, does it end up working? And so you just kind of have to reason about it, and you have to say, does this make sense? And then if you think it makes sense, you have to try it out, and if it doesn't work, then it doesn't work. Really, trial and error is like the metric by which a lot of people do these things.
Another way to make our network smaller is to use different embeddings of words that aren't one-hot encoding. So if I wanted, there are sort of pre-trained word embeddings. For example, there's a famous one called word to vec that will give you very similar vector representations of words that mean similar things. So like the word warm and the word hot, in one-hot encoding, they're just like completely different. There's like a one in a separate place for each of the vectors. But in sort of a word-to-vector embedding, they'll be very similar vectors, and the vector won't be as long as the vocabulary says.
Okay. Does anyone have any more questions about the theory before we explain the implementation? Hopefully the theory will become more clear as we do the implementation. So, yes?
Not sure if this is really important, but could you use a vector that's roughly as a logarithm and fill them in and use the logarithm of the size of the vocabulary, and then
You're saying like not one hot encoded have a full combination of ones?
Yeah.
You could do that. I think the reason why people don't do that is now those combinations may not be linear. I could be wrong on that. It's definitely not something that people conventionally do. Theoretically, you could do it. But presumably now your network has to learn more complicated. Like, it has to come up with some more complicated function to actually transform it into useful output. So it might be that it works, it might be that it doesn't work. And actually, it's interesting. I'd have to think about it more. But yeah. One thing that we didn't actually touch on that I feel like is important before we continue on to the theory or the implementation is how big the RNN state should be. So if the RNN state is a vector, then obviously the size of the vector means something, right? So, for example, if I am trying to do a copy problem where I input, let me grab the thing real quick. Okay, so if I'm trying to do a copy problem where, let's say, I have some sequence, and then this one says, okay, start generating the, like, clone the output, and this output should be the same thing as here, then presumably what the network needs to do is it needs to memorize what it saw, right? And so one way that it might do this would be if you got 10 inputs and the cell state was of like 10, then it could just put some number in each element of that cell state corresponding to which input it came from, and then like remember it that way. That's not actually in practice what happens, but it's like theoretically one way that it could happen. And so, but if you had a cell state of 9 and you needed to remember a sequence of like 10, then it might be that it can't encode all that information. And so what this essentially means is that the smaller your cell size is, the fewer parameters your model has, the quicker it's going to run. But because you have fewer parameters, it's a weaker function. It's a simpler function. And so basically your cell state, the state size of that vector, the size of the state vector, is directly dependent to how complex the model is. So larger it is, the more parameters, the more complex. The smaller it is, the less complex, faster it will run, but it might not be able to fit the data. The other way, again, to solve that is having more cells. And so these are trade-offs. Do I opt for a larger cell state and just have one RNN cell, or do I do a smaller cell state and have several RNN cells right after each other? They both do subtly different things. So you just really have to think about like what is going on and why you do one thing and then test it out. Okay, with that though, I think we should continue on to the implementation. Okay, so let me post this code onto, oh my god. Let me post this code onto Slack so that everyone can view it. now to Slack. Let's make computer stop time. Yeah. So just go ahead and unzip that folder once it finishes uploading. It should be up there now. So go ahead and unzip the folder, CD into it using terminal, source activate TensorFlow if you're using Anaconda, and then just run Jupyter Notebook.
Yeah, as usual, if you have any problems getting this to work, you can just talk to me or
Will
anyone.
the TAs go ahead and just stand up so that everyone can see them real quick? So those are our TAs. If you, for some reason, have a problem getting it to work, just ask one of them. Okay. Does everyone have the notebook open and ready to go? If you don't have that, please raise your hand so that I can wait for you. Okay. Do you need a TA to call you, or are you good? You're good? Okay. All right, so I'm actually going to use this now because my throat is getting really sore from talking for so long. But here, let me pull up the projector. Okay, so basically, in that folder, there should be a file called Alice with periods.npz. This is going to be what contains the actual data for Alice in Wonderland. And you can ignore the RNN.py file. Inside of the save folder, there's a couple other files, and these are files used by TensorFlow to restore the trained model. So what we've done is we've trained this over the last day or so that it'll go faster for you guys. And the code will actually load these values and restore the values for the TF variables inside of TensorFlow. And then obviously this is the notebook. So opening up the notebook, obviously the very first thing we need to do for any of these programs is to import TensorFlow and NumPy. Then what we're going to do is just to make sure that everything is consistent between everyone, we're going to seed the random number generator. And then we're going to, so the first bit of actually importing code is right here. And basically what this does is it takes a list of words encoded as like a string, and then it's going to turn them into a list of numbers. And what it's going to use to do that is some additional list of words called vocabulary. And so, for example, to construct the vocabulary, what we've done is we went through the entire book of Alice in Wonderland. For every word that we detected, we added it to the vocabulary, for like every new word, right? And so what this means is we've compiled essentially a dictionary in the literal sense, not the Python sense, of what each word in like we've listed out every unique word in Alice in Wonderland. And so if we, what the result will become of this function is which index of the vocabulary this word was. And so this is how we convert from a string to a number. So that's the helper function up there. Here is where we actually load the data and then pass it through that helper function. So in this case, we've printed out, Alice loaded is the actual array of words. So here's the array, and you can see that this is the beginning of Alice in Wonderland. So, and this is only the first 100 words because that's what I specified here. And then Alice in Bed is going to take this and turn it into a matrix of numbers down here. And so the shape of this is, what this code does is it turns it from a list into a matrix essentially, and splits it into training and testing data. And this is because with the RNN, we want to operate on sequences of a fixed length. And so we've essentially just chosen the arbitrary length of 25, and we've said, okay, we'll just chop this up into 25-unit sections, and then just list them all out. And so what this is essentially going to mean is that we have 842 sentences of like 25, and then each sentence has 25 words in it. And so when we actually run the RNN, the sentences are going to become part of the batch dimension, just like if we had a whole bunch of images that we wanted to operate on once, those went into the batch dimension. So each sentence is its own sample from the data set, and that's going to go into the batch dimension. Does anyone have a question about like why this is shaped the way it is, or what these numbers are, before we continue? Okay. Okay, so obviously now we have to construct the actual TensorFlow code. Everything up to this point is just data encoding. So this reset default graph function is here just in case if you rerun the cell. And then obviously we want to set the random state for TensorFlow. Then we need to actually define our inputs. So this X placeholder is just going to have a shape none comp sequence length. And the reason why it's shaped none is because we want to feed in sequences, or we want to feed in any number of sentences, right? It doesn't matter really how many we feed in, because we're just doing the exact same operation on each of them, except in parallel. So that's why it's a shape none. And then sequence length, obviously, is because we have to work with a fixed length sequence. So I can't all of a sudden start feeding in sequences of like 27 without breaking things. So that's why it has to be in like 25. And of course, if you want to change that, you can just change that value up here. All the code will still work. Okay, so then what we need to do is we need to actually one-hot encode our inputs. And so that's what the tf.onehot function does. So the depth parameter is essentially telling you how large your vector should be. And since we are using a vocabulary, it should be the size of the number of elements in the vocabulary. So back up here, I computed what that value was right here. So I said, give me however many words are in the vocabulary, and we're going to call that embedding size. So that means that our one-hot vector is going to have the shape of batch size, sequence length, and embedding size. Then we need to actually unroll the network. And so this is the rather complicated part of the code. So what I'm saying is I'm essentially going to have state vectors that are this big. It's a little bit different because, like I said, we're not using a simple RNN like over there. We're using a rather complicated RNN called an LSTM. The way that you enroll the graph is still the exact same, and in fact, all those images over there are still accurate. But the actual functions that are used to generate the state and generate the output are a little bit different. But they're kind of in a black box that we're not going to cover today, and TensorFlow has already implemented that for us. So just what's important is to keep track of like the flow of the state and the inputs and outputs through the model. So essentially, num units is going to be how much memory the RNN cell has. And if we were using a simple RNN cell, it would be exactly equal to the size of the state vector. And then we want to have 3 RNN cells stacked together. So in that example, there were 2 RNN cells stacked together. In ours, we're going to use 3. And so each one is going to have 256 size of the cell state. And so we just go ahead and construct those right here. Basically what this is doing is TensorFlow, we're not adding any operations yet to the TensorFlow graph, but we are kind of telling TensorFlow what these cells are going to look like, so that when we do add operations to the graph, it knows in advance like what to add. So in this case, the parameter that we give it is, we're telling it that cell size. And we're also telling it that we want to use an LSTM rather than like just this very simple RNN. So if I had wanted to, I could just make this an RNN cell, and everything should still probably work. But for now, we're going to use LSTMs because they're more powerful. And, okay, so now we need to actually define the initial state of the RNN. So for every sequence, we're going to just set the initial state to be 0. And so the way that we do that is we could call tf.zeros, but we're actually going to call the 0 state function associated with the cell. And that is because, again, with an LSTM, the state is more complex. And so it's not just one vector for the state, it's actually a couple vectors. But where it's abstracted away from us, we don't need to care about how it works. We just need to call the 0 state function. And so we also need to tell the batch size, because obviously state depends on each element of the batch. There's going to be a different state associated for every single different element of the batch. So that's where we need to provide that. And so, yeah, and I can actually view what this is. So if we take a look at what our state actually is, you can see that it's more complicated than just a vector. It's some tuple of, it's actually 2 state vectors. And so each of these vectors have a size of 256, and that's what we set num units to be. So again, I don't want you to worry too much about this, but I just want you to see that, like, it's not necessarily magic. There are actual computations happening here, and if you want to, you could read more about how LSTMs work to understand why this is the way that it is. But for right now, just think of it in terms of the flow of states and inputs and outputs. So, okay, so here's the part that is significant. This is where we actually do the enrolling. So what we're going to do is we're going to have a list in Python, not in TensorFlow. This is going to be a Python list that keeps track of the outputs for every single time step. And so this list is going to be a list of tensors. They're not going to be a list of actual values, just of the tensors themselves, so that when we do session.run, we can use the things in that list to request things for each output. So what we want to do is we want to iterate from 0 to 24. Recall that our sequence was of like 25, and the reason why we go from 0 to 24 is we have to shift that sequence over. And so when we do that shifting, right, because we want to predict the next word, so that's why we shift it. When we shift it, it means that it can't be a full length 25, it has to be a length 24. It might be a little bit more apparent as we go on. So what this does here is, actually let me discuss this and then I'll explain what this line does. So the very first thing that we do is we want to feed some input into the first cell. And so what this is doing is, here's our batch dimension. We want to take everything from the batch dimension. We only want a particular time step. So in this case, for the first loop, I is going to be 0, so we want the 0th index of the sequence dimension. And then this is the embedding dimension. So obviously we still want the full embedding vector. And the initial state, we already set up here, and that was just going to be like the vector of zeros. And so the initial state is just something that we just initialized to 0. And so what this is actually doing is it is generating the structure of the RNN as I call this function. So not only does this function output the output and the state, it also constructs all the operations and tf.variables needed to do the output and state. And if you recall a couple lectures ago, I stressed the importance of using tf.get variable instead of tf.variable. And that is because if we want to tell the cell when we don't want it to make new variables, right? So the variables should always be the same at every time step. If you remember, this is cell 1 and this is cell 2, but this is also cell 1 and this is also cell 2. So we don't want new variables for this. We want the same variables here and the same variables here. So what this essentially means is as we do one pass through the for loop, we're constructing all of these, and then when we get to the next iteration of the for loop, we're constructing these, and we don't want it to get new variables for these. So the way that that happens is this line right here. If we've already done one iteration of the loop, we tell it to reuse any variables. So when the code inside of cell 1 calls tf.getVariable, instead of constructing a new variable, it's just going to reuse the variables it's already constructed. And so that makes sure that the weights are shared when you enroll it. Okay, so the next bit, we just passed the previous output from cell 1 into the input for cell 2, and we passed the state from cell 1 into the input state for cell 2. And we do that, I'm really losing my voice, I'm sorry. So we do that again for cell 3, and what we end up getting is we get our final output and our final state for that time step. So each of these are equivalent. So as you can see, since we have an output and a state for every time step, that's why we had two lines here. There's an output and a state. And again, output and a state. So this is the final output, this is the final state. Okay, and then obviously we want to generate a sentence, so we need to keep track of our outputs. So that's what we do here. And this tf.stack operation, essentially, what it does is it takes a Python list of tensors and turns it into a single tensor of one dimension higher. So, for example, every element of our outputs list has the shape it has the shape batch, comma, embedding size. And what we want to do is we want to turn it into shape batch, comma, sequence length, comma, embedding size. And so that's what tf.stack does. It says, okay, you've got a list of tensors, stack them all into one tensor, and we want to put that stacked dimension in the second dimension, which is axis equals 1. And so what we end up having is a tensor of shape batch, comma, sequence length, comma, output size of cell 3. So I'll show you that right here. Okay, so yeah, so that's the shape of outputs. Okay. The next thing that we are going to want to do is, let me rerun this code real quick, I'm sorry.
You have a typo there.
Where?
Up at the top of this, right, nope, down, there we go. LSTML, you should use C, LSTM, so.
Oh, thank you. Yeah, that's fine. Okay, so this is a little bit of a sneaky thing. When I printed out outputs, it showed the wrong size, and that's because I reassigned outputs to something else later on. The actual size of outputs is here. Okay, so you may notice that the last dimension is only 256 instead of the full size of the embedding. Obviously, in order to be useful, we need to generate words. 256 isn't a word because it's not the size of our vocabulary. So we need a way to convert from that size back to our embedding size. And so the way that we're going to do that is we will use a softmax layer, just like we've used in all the other types of neural networks. So, real quick, obviously the softmax layer has a weight matrix, right? And so the weight matrix would always have a particular shape. So suppose I want my output size of the softmax layer to be of like 1,000. What would the shape of the softmax matrix be? So here is the thing that's getting fed. What do you think I would make the shape of W in the softmax layer be? Any guesses? It's okay to be wrong. Yes.
256 by 1,000 or 1,000 by 256.
Yeah. Yeah, so our W is going to need to be of shape 256 by 1,000 because obviously we want to operate on this dimension, and so that's why the first dimension is going to be length 256, and since we need to turn it into the embedding size, that's why we want our second dimension to be the embedding size. So to actually do that, what we're going to do is we're going to construct our W and B right here, and our shape is described right here. So we go from the size of the output to the embedding size, and obviously our biases are also of size embedding size. And then in order to actually make this work, normally, for example, if this was coded NumPy would just broadcast a matrix multiplication over the batch dimension. If you don't know what I'm talking about right now, don't worry about it, by the way. If you do know what I'm talking about, then NumPy would normally broadcast the matrix multiplication over the batch dimension. However, for some reason, TensorFlow doesn't do that right now. It's something that's probably going to change very soon because a lot of angry people, including myself, are complaining about it on GitHub. But basically, in order to get around this limitation, what we need to do is we need to reshape the tensor so that it's in the shape of the matrix instead of like a 3D tensor. So what we're going to do is we're going to make the second dimension have the output size shape and then merge the batch and sequence length dimension together. And so this command does that. And so now we have some flattened tensor, and I can show you the shape of that right here. And so the reason why there's a question mark there is because originally we didn't know how big the batch dimension would be because we set it as none. So this is essentially none times sequence length, and then that's also none. So it puts a question mark there. But when you actually run this, suppose the batch dimension was of length 10, then this dimension would be of length 10 times 25, so 250. So once we've done that, we can perform the actual matrix multiplication, which is right here. Then we're going to want to reshape it back into the original shape of the tensor, and you can see that right here. So now it's back into the original shape. I misspoke, by the way, it's size 24, not 25. And you'll notice that now instead of size 256 here, it's the full size of the embedding. And so now what we've essentially got is we've got a tensor of scores. That is, once we add the bias, we've got a tensor of scores. And we want to turn those into probabilities, so we just put them through the softmax function. So that's what we do right here. So at the very end, we have this. So again, we get the tensor the same shape, but this tensor is going to be all values between 0 and 1, and all the values along the embedding dimension will sum to 1. So we treat them as a probability, and then we essentially just put that through our loss function. We have some matrix of shape scores. Remember, we pass the raw scores before the softmax function just for numerical problems. There's like some accuracy problems if you don't do that, and so TensorFlow requests that we pass the raw scores in. And so we pass in the scores, and we also pass in the labels. And so the labels are going to be the same shape of the scores except without the embedding dimension, and that's because the labels aren't one-hot encoded. And that's just for computational efficiency. What it's internally doing is it is going to compare the one-hot encoded representations, but it obviously takes up more memory, so we want to avoid having to pass that. So that's why it doesn't have the embedding dimension. So, so that is all the code we need to construct the graph for training. Now what we need to do is actually actually run the training, so actually update the weights. So obviously I have to create a session. I also make this tf.train.saver object, and this is what we use. It's a simple way to save and load models, and we're going to be using this to load the weights that we've already computed for you. So what we do is we attempt to load the weights. If your code actually succeeded, you should see restored model down here. If it didn't succeed, then it will say initializing model. Does it say initializing model here for anyone? Could you guys check that real quick? Okay, so as long as you copy the zip file correctly, it should. The only time it would say initializing model is if the weights file didn't exist. And so in that case, it would just start from scratch. And it would still work, but it would take you a whole day to get to the same accuracy that we're looking at now. So, okay, so now basically just for demonstration's sake, I've set this to run only 10 epochs. Obviously, if you were actually training this, you just set it to sys.max size, so you want it to run forever. And then I just loop through the data. So at every epoch, again, an epoch is a single pass through the data. At every epoch, I shuffle the data set, and then I put it into batches, and then I perform mini-batch gradient descent in the exact same way that we did for any of the other neural networks that we've discussed. And the reason why this works is we've set up the loss function, and TensorFlow knows how to compute the gradients, so it just does, it does the math for us using the optimizer that we defined right here. So we run that, we do session.run, train step, and loss. So that's going to give us, we don't care about the value of train step, and then we do care about what the value of the loss is. So we take a look at that, and then we average that loss over the whole batch. And then we just print out at every epoch how the loss is doing. So as you can see here, the loss did get a little bit better, not by much. And as best as we can tell, the loss isn't going to improve any further from here. We tried running it for a day and a half, and it stayed pretty stable here. So for this particular architecture, what you're looking at today is probably how good you'll get for our particular choice of hyperparameters. Obviously, that's something that should be experimented with if you're interested. Okay, so now we have to actually generate the text. And this is a little bit trickier because we're actually going to have to recreate the whole graph again just to regenerate the text. And the reason for that is the way that I've defined my model, if we look up here, is that at every time step, I already know what the next output should be, and so I'm just feeding that into the input. But when we're actually generating text, we don't know what that is going to be. We have to use the previous output of the model. And so that means that we're going to have to change our actual architecture here, and you can't just rewrite architectures in TensorFlow. You have to either totally erase the graph or make a completely separate subgraph, essentially. So we are going to essentially reconstruct the whole thing, which is it was definitely tedious for me to program. But essentially the only difference here is more or less in this beginning bit. So what we're going to do is we're going to tell how many different sentences to generate, and we're going to specify that with a placeholder, which just holds a scalar value. And essentially what this is going to become is the size of our batch dimension. Then we pick a random word from our list of words. Essentially the way that we do that is we just generate some number up to the size of embedding size, right here. And then we go ahead and reuse the softmax variables, and then we define a helper function for the softmax function. And this is just going to make the code a little bit neater to read. you may be confused as to why we're doing the softmax before we do the unrolling, and that's just because we're going to use it in the loop for the unrolling. And so in order, obviously in Python, in order to use a variable, you have to declare it and define it first, just like any other programming language. So that's why we do it up there. Now we have to actually unroll the cell, or unroll the RNN. So again, we define the cells in the exact same way. An important thing to note here, though, is that we've specified this reuse equals true flag. And so what that means is TensorFlow will actually throw an error if we ever call tf.getVariable and it doesn't already exist. And that's good because it means that it'll help us catch any mistakes we made when we programmed. So the session is still active, right? I define the session when I train, and so this is all still running under that session, and so the variables are still loaded in the session. So I can still call tf.getVariable, and it'll just use whatever values it had when it was training. So I just, again, make the state 0. You'll notice that I've actually, this is essentially aliasing initial state and state, so I've got two different variables that both point to the same thing. And the reason why I've done this is because you can actually, if you want to experiment with states that are non-zero for the very first word, you can manually use initial state in your feed dict option for session.run. And so you can actually feed it whatever you want and see what the RNN generates. But for now, we're going to keep it simple and just have the very first word start with the 0 state. So then what we want to do is we want to, so we've already selected the word at random, and so we're just going to say, okay, whatever word we selected is the first word we generate. So it's going to be the very first word of the generated sentence, and what that means is I have to turn it into a one-hot encoding to be able to be consistent with how we define the architecture. And then I'm going to assign that to previous word. And previous word is just a variable that we're going to use to represent the previous generated word when we do the unrolling. So previous word will be each of these outputs, and we're going to feed them into the input. So, and I mean, that'll be pretty apparent when we actually do the loop. So obviously we want to keep track of all our outputs. So our first output is the word that we selected at random, and then we go ahead and we actually pass that through the network. So our very first input is from the last output. We input the last state, and then we output a new output and a new state. And so note that previous word and output have different sizes. Output has the size of, usually it's the size of whatever num units was. So in other words, the size of the cell state, usually. And state, obviously, is some state that is held by the network, which is related to the size of the cell state. And in the case of the simple RNNs that we covered before, is exactly equal to the size of the cell state. And then we just pass that through. And this is the exact same way that we did it for the first one. It's just now we have a different source of our input. And then finally, we take that final output and we pass it through our softmax layer, just like we did before, except now this is inside of the loop. This is functionally equivalent to the way that we did it before, but because when we did it before, we could just generate all the outputs at once, and now we can't. We have to do it inside the actual loop. So it's a little bit slower, but it's still mathematically identical. And then we just generate an output word, and then for our actual outputs, we just append that and then make previous word equal output word. And so this just cycles through the whole sequence and generates the whole thing. We can also keep track of the final state in case if you want to continue to make longer sequences. So you could do when you run the session and generate a sentence, you could also request the value final state, and then you could run it again and pass final state into input state. And that way it'll continue to generate a sequence using the same thing. And then, again, we just stack together the outputs into a tensor. This has shape num to generate, which is essentially our batch dimension, the length of the sequence, and the embedding size of the vocabulary. And then to just make things a little bit more user-friendly, we go ahead and we take the argmax along the embedding size dimension. And essentially what this is doing is it's saying, give me the most probable word that you've predicted. And so it's looking for its best prediction. And so that's the one that we're going to use for generated sentence. So now we've defined the graph, but we haven't actually run anything through the graph. Obviously we ran things through when we trained, but in terms of like the new graph that we've constructed for inference and for actually generating sentences, we haven't run anything yet. So now we're actually going to generate some things. So we just call session.run. We request the value of the generated tensor, and we tell it, I want you to generate 10 different sentences. And so what this is going to return is, it's going to return, I can print this real quick. So you can see that it returns just some big array of numbers. Obviously numbers aren't very helpful to us, we want words. So we need to actually convert this back into words. And so I'll just show you the shape of results real quick. And so you can see that we've got 10 sentences, each sentence is 25 minutes long. So what we're going to do is we're going to, if you guys aren't familiar with this notation, it's essentially called the list comprehension in Python. And this is essentially a way of generating lists by looping over other lists. And essentially what's going on here is it's saying, okay, the outermost loop is looping over each of the sentences, the innermost loop is looping over each of the words in the sentence, and then you take the number and turn it and look up the correct word in the vocabulary. And so now we can loop over all the sentences and print them out. And so this is what we get. And like some of these are really good. So for example, these are actually a little bit different from the ones that I originally did, which is interesting. Go ahead and rerun this, but in the meanwhile, you can just kind of look through those results. In my experiments, basically what I saw is that there were a couple of sentences that were directly copied from Alice in Wonderland, and the way that you can think about that is essentially the model has learned how to encode whatever sentence it sees within the size of the state vector. And this is a form of overfitting, not necessarily something that we want to do. Like if we just wanted to exactly word for word recreate Alice in Wonderland, we don't need an algorithm to do that, we could just literally recreate it. What we really want to happen is for there to be new sentences that seem like they're from Alice in Wonderland. And so occasionally that is what you get. Sometimes you get unlucky. Like, for example, tumbled and existence howled the game, the lizard in the distance, and as the question was sitting on the next, so too much even hits. That's just not, that's nonsensical, right? So, and so what this tells us is we've probably made a pretty bad model. And so if you wanted to, you could go through is, what you could do is you could go and you could look up, okay, how can I improve this model? And so a couple of options that you have are A, messing with your hyperparameters. So you could try having a larger cell size. You could try having more or fewer layers. You could try adding a regularizer, like L2 regularizers, like we discussed before. Or you could try a different, more advanced type of RNN cell. So for example, instead of using an LSTM, you could use a neural Turing machine or a differentiable neural computer. By the way, TensorFlow does not have implementation for those, so you're not going to be able to do it simply like this. But it is technically something that you could do. Those, by the way, are super complicated architectures that you could talk to me about if you want to, but they're like well beyond the scope of this course. The other thing, and the more likely approach that you should take if you wanted to improve this, is rephrase the question, essentially. So right now, the question that we've asked the network is, given your last output, generate a new output. And the way that we trained it is, given the current word, predict the next word. Actual industry standard things do something called a sequence-to-sequence model, where you're essentially, it's this type of model, the one in the middle right here. So it's So our model looks something like this, but better models oftentimes look like this. So they'll have some start token, they'll have the sentence, they'll have some stop token, and then when the stop token happens, the model will start outputting a new sentence with the start and the stop token. And so this is a way of kind of teaching the model, kind of like how you teach a person. Like, if I were to go to a person, I would say, here's the full sentence, now change that sentence, instead of saying, here's a word at a time and change it. So they're subtly different, but they're important differences, and empirically researchers have found that sequence-to-sequence model tends to work better, which is that one up there, not the one we did. Yeah, so that pretty much concludes our coding portion. Do you guys have any questions on how I implemented this stuff? I know it's like very lengthy and kind of complicated. So, did you guys have any questions on what you saw in the code? Okay, cool. Yeah, so that concludes our session. Thanks for coming. This is the very last one of 4. So hopefully you guys found this informative. I will just want to mention, next semester we are recruiting, and in particular CBS really is, at least for Yuji and myself, we're really looking for people who have experience with deep learning. So coming to these workshops is like very helpful for that application process. So if you are interested in joining the team, this gives you a tremendous leg up if you have come. So yeah, I will be posting actually, if you are interested in joining the team, just shoot me a direct message within Slack. And obviously we can't take you on this semester, but at least I'll keep you in mind for next semester. And we'll kind of prioritize you guys through those interviews. So yeah, thank you for coming. If anyone has